Good afternoon, everyone. Before we start, a warm reminder to all of you that please check the assignment and also lab report where I already post in the Google Classroom. So if you have any questions regarding the especially the marks given, you may email me personally. Okay, and for all those comments or questions that I put in your assignment or lab report, you don't need to reply me. Okay, um, and please do please perform your personal checking until this Friday, 5 p.m. Okay, because after this Friday, you may download as well for your own archive. And after this Friday, 5 p.m., I will, change the privacy of the folder lah. Okay, that's all. So if anything, if any questions lah you want to ask, you may ask, but make sure you come with evidence lah. All right. So remember only this Friday because I have to key in the mark by maybe this weekend somewhere around there. Okay. So for today, these sections we will do revisions. We will do revisions, and for later on 4:30 we will have our tutorial class. So we will complete the rest of the tutorial. Okay. So for today, this we will do the revisions for chapter 3, and then yeah, starting from the initial chapter first. I think chapter 1 is about the 5 elements in multimedia. That one should be okay. Not really many items for you to revise. Yeah, but of course, as I mentioned, you don't need to memorize all those um, different software, especially introduced in chapter 1. You don't need to memorize the software, okay? But at least you have to know uh, JPEG is for image, not video. MPEG is for audio. MPEG maybe layer 3 is for the audio, this and that. Okay, those very, very common you have to know. For example, PNG is sort of extensions which is specifically used in the image. Okay, okay, so let's move on with this color model, color formations. So for this chapter, we mainly focus on the RGB, CMY, K, and also HSI. Okay, I believe we already learned the YUV, YIQ, YCBCR, and perhaps you all are quite well versed now, especially recently because you all just complete your lab and also assignment. So um, RGB CMYK is the very, very basic in image processing, especially when you are dealing with 24-bit true color. Of course, we are dealing much more, more on the RGB instead of CMYK, because the RGB would be the most, I would say most common color model used for the uh, monitor display or almost all the digital display. Usually we will use the RGB, but for CMYK it's mostly used in the printing industry. Okay, and something that you always have to know is that um, RGB is used in one domain and CMYK is used in what domain and what's industry. And initially we only have CMY, we don't have K. Okay, and K is about black color. Okay, so what is the motivations to have K later on? So you have to know this one. Okay, so I will not follow page by page. Color can be defined by choosing three primary color, which is P1, P2, and P3 for red, green, and blue, respectively, where RG and B is the mixing weightage. So, the color value here would be you have three layers lah. First layer, which is R, G, and B, respectively. So in each layer, you have different value in terms of R. You have different value in terms of R value, G value, and B value. Since you have 256, which means 0 to 255 value, multiply with 256, multiply with another 256, you will have around 60 million value. Okay, so this is the basic attributes in terms of RGB. Okay, so with these 16 million, basically you have all the color variations. You can form whatever color variation you have by just simply put together, superimposing the red channel, blue channel, and green channel. So these are all three channel are known as primary color, which is red, green, and blue, and will produce a wide range of spectrum. So color model, color space, color system, and color scheme are synonym lah. Okay, so all are synonym. So if let's say but the most common one would be color model. If let's say you have color space, color system, color schema, it's referring all of these are referring to the same thing. Okay, please do not confuse. So it provides the coordinate system that are defined by three tablets numbers, which is uh for example in MATLAB you have maybe 2550 200 100. Okay, the arrangement is the way in RGB. Will not make sense. So gamut is the range of color lah, something like this, different color range. Depends on what color space it is. If it is RGB, then you have a different gamut. For YCBCR, you have different gamut and up. And same goes to HSIs and HSV. Okay. So RGB is the primary value for three corner. So you have a XYZ exit. Of course, you can interchange this one. We don't have a we don't have a fixed criteria or any fixed rules say that Z must be R, this must be G. No such thing. Just that any value of this, um, I mean, this exists is just to mention that you can actually formulate or place the RGB in three different exits. So the secondary color would be cyan, magenta, yellow. So it's CMY at the other corner. So black is the origin or so-called K is the origin and white is at the corner farthest from the origin. Um, Basically you can always draw the no matter X, Y, and Z. So this is always the black color line. Okay, and um, yellow, magenta would be somewhere around this corner. And the corner here would be white color. Okay, something like this. Later we have a chart which is in 3D lah. It's better to illustrate this one. Okay, for this one. So you have your red color, green color, blue color. So red color here would be always remember RGB. So this is value 111, and the black is the origin here and the white is here. So between blue and red would be magenta, between blue and green would be cyan, and between green and red would be yellow. Okay. It's okay for you if you want to memorize it, it's okay. But if you don't want to memorize it, you can actually deduce from the formula, white. So you have 111 minus by the RGB value. So you would have CMY. You can actually deduce from here as well. But make sure your brain can function well whenever you want to deduce this formula. Okay, else you can just memorize it. But nonetheless, you have to know the background theory. For example, why blue and red comes with magenta. Okay, you can explain using this formula. Okay, so by subtracting something else from white color, because 111 is white, right? Zero is black. So by subtracting something else from the white color, so-called the subtractive mixing. Okay, so it is not additive. For the RGB is additive because you add in something else. For example, red add with green, you get the magenta, and then for red add with add with green, you get yellow. Add red Add with blue, you get magenta and so on and so forth. Okay, so this is so-called additive. Okay, the motivation is there lah. When you subtract something else from the white color, so you would get so-called the secondary color or the CMY. So you have two different mixing, additive and subtractive. Um, you have to know the motivations here, why it is so-called additive, why it's so-called subtractive. Because the question may be asked, define additive or define subtractive, something like that. Okay, and you have to know why it is additive, lah, not just a naming, give, and simply give to RGB or any CMY. So you have to know the applications for RGB and CMY. Of course, the application is not restricted to monitor and printing lah. Some other I mean elsewhere, just that you have to know some of it. So the magenta is basically red, plus blue plus green, you get cyan, green plus red, you get yellow, and in another way, you can also deduce this one by magenta is actually white minus green, white minus something else. So you have one minus by R, G, and B. Okay. So additive mixing, primary RG and B are three primary color used to produce other color. Most of the color in the visible spectrum can be created by mixing these three primary color. So this is called additive color properties and is worked by mixing primary color for emitting light. So mixing red and green, yellow, and so on and so forth. So this is how you get it. The same theory is applied to the televisions, whereby you have three different cathode to shoot out the beam, produce the beam in red color, beam in G, beam in B, and then all these three beam add up together with different weightage. For example, 200, for example, 100, for example, 100, you will get one color. Okay. So the beam is keep on mixing in such a way in order to portray the entire image in the televisions lah. Okay, this is what we have learned in the last chapter, chapter 11. Yeah. Okay. So you have a CRT, cathode ray tube. So this is it's used the electron gun to project the beams and mix together to a specific point. So you will able to see a specific color. Okay, so this is so-called the RGB mixing lah. So subtractive mixing, although we are using the word mixing, but nonetheless it is about subtract something else from the white color. Okay, so cyan pigment absorb red color, magenta absorb green, and yellow absorb blue. Okay, um, you don't really need to memorize this because RGB is CMY. So basically, this one absorb this one absorb this one. Okay, you just write in the uh ascending order, then should be no issue. Okay, remember the word absorb because sometimes absorb and emit is different things, and you have to explain. Since this is an engineering course anyway, so you have to explain in such a way which is comply to the physics rules. Okay, so whatever we see, no matter the white color wall, the black color hair, and etc., those color are reflecting from the object, which mean for example, the red color bottle. The bottle absorb all others color except the red color. So that is why the red color is reflected away from the bottle. That is how you see the red color. Okay, if the bottle absorb red color and maybe reflect green color, so you will see the bottle as green color. Okay, make sure your writing is correctly sound in terms of physics. It is not that the red color bottle display red color. Okay, it did not display anything but reflect the light, the red color, right? Okay, to be accurate is the spectrum or the wavelength. Okay, subtractive color mixing is based on reflective color rather than emissive color. So reflected color refer to color from light reflected from a surface into the eye. So So used primarily in the printing industry by printing the three subtractive color in different proportion on white paper. Okay, so this is the main applications here. And another thing is that I did mention why there is a K, because initially we don't really need a K like ideally like. That is because when you have zero, when you have a full full yellow and full magenta, you should able to get a black color. But ideally, the color is never a pure color like. So um by adding up the mathematics, yes, you will get maybe 255, 25, and 255, or maybe 000 and 0 to 3 zeros. But in practical, you will never get a pure color. So that is why the manufacturer they instead use a K. So K is a black color, and this K is actually you can actually get, but by mixing the CMY, but just that it is more likely to appear as a dark gray color, very dark gray color. But instead, it is not a black color. Okay, and black color is widely used in printing industry, especially for all the fonts, all the background, all the texture, all the outlines of something else. Those all are in the black color. So mixing the CMY alone may not be that practical, and maybe such mixing might cause a delay in time, uh, printing time especially. So that is why the K is being added in to CMY model, because CMY model is usually used in the printing industry. So later on, K is being added in as another independence color, so that whenever the black color is needed, so it will print out the black color instead of making C, M, and Y. So color model in on image, each color model use three primary color. The coordinate system describe the mixture of primary color. So you have RGB, CMY, or CMYK, HSL, HSV, and HSI. Nonetheless, all these three are very identical. Very similar, like I should use the words. But identical, it is not really identical, because um, they have a different gamut and also a different architectures. So, for example, some have a cone shape, some have a, what shape is it? I'm also not sure. So some have a different shapes, okay, but nonetheless, the overall presentations, the idea of HSL, HSV, and HSI are more or less okay. So RGB, based on additive mixing of three emitted light source, color is represented by a numerical triplet specifying RG and B. So the value of RGB is between 0 to 1. This is so-called the normalized value. Okay. Whenever you see the equations, which, for example, R prime plus something else, or G prime, in an equations whatsoever. So whenever you see this prime, that is a normalized value, which means you need to divide by the maximum value. In this case, the maximum value is 255 lah. Okay, this is the very cliche way to normalize anything else. Okay, if you want to normalize something else, normalize, which means you put the range into 0 to 1. Okay, into 0 to 1. Usually put in this way lah. Okay, 0 to 1. So when you put the value into 0 to 1, basically, the maximum value should have 1, the minimum value should have 0. So the idea behind this one is to divide by the maximum value. For example, you have 255, right? The minimum value is 0, right? So 0 divided by uh, um, the divide by 255, you get 0 lah. Okay, it's impossible to divide by 0, right? You will have a syntax error. And 256, max error. 256 divided by 255 divided by 255, you will get 1, exactly 1. Okay, and this is how we perform normalization. No matter in what applications, normalization is always in such a way. Okay, so it depends, not a must, it's between 0 to 1. Sometimes, most of the time, it's between 0 to 255. And in the case of case that you perform any calculation examinations, I would suggest you all to use four decimal place, especially for calculation in such a range 0 to 1. Okay. The reason is that it's not so practical that you use only one or two decimal place. For example, 0.77 is not so practical lah. Because when you're using four decimal place, the calculations of the final value would be more likely the same. Okay, of course, I mean, the the more value that you append would be more accurate lah. But it's pointless to you have a long value at the behind. But when you use your calculator to perform the calculation, it's okay for you to use the whole value. Okay, and then later on only give me the final answer in four decimal place. Okay. But for those value which is supposed to be integer, for example 0 to 255, um you don't need to give me dot 0000, you don't need to give me something like that. Just that those value is I mean, especially for those value which is supposedly to present in decimal place, then perhaps all the calculation should be using four decimal place. Okay, if you perform the calculation only in two decimal place, and then later on, for example, maybe 0.1234, but you only perform your calculation using 0.12, and then later on in your answer you give me four decimal place, the answer might not be so accurate lah. Okay, the idea of giving, I mean, using the four decimal place is to ensure that your answer supposedly very close to my answer. Okay, the marking scheme. Okay, so this is the reason, not that you just give me the final answer, in decimal place for four, just to fulfill what I request, but actually, end up the answer is not that sensitive to, I mean, or eventually close, lah. Okay, because sometimes you use two decimal place, it might have a deviation, I mean, discrepancy of maybe 0.01, something like that. Okay, if let's say you have discrepancy of 0.02 to 3, it's quite big lah to me. Okay, so it specify how to mix the three color lights of red, green, and blue to produce various color. So this is the color block. Um, you have to know the relationship between the color blocks like, okay, so you should able to explain why in grayscale, especially in MATLAB, when you have, you convert the image to grayscale, and then you click on the image to display the index or the intensity of a specific pixel. So what is the reason behind that the index shows is always same in value? For example, 100 is always same in value. For example, this is grayscale. So if you move the your mouse, hover to, I mean, click to another pixel, maybe the pixel is 210. Why is the reason? Why is the reason? Uh, the MATLAB display you three different same value. I mean, sorry, the three same value. Why? Why not just display only one? That is because the reason is that in when you are in grayscale, actually you are still using the RGB, just that RGB is always in the same value. For example, let's say 100. So let's say this is 0, this is 255. The maximum value here is 255, let's say lah. Okay, so if let's say you have 100 somewhere around here, so and you have 100 in red color somewhere around here, and 100 from green somewhere around here. So all when you plot all these, you will get this point, right? Okay, this is something in Cartesian plan. Okay, you let me put in two-dimensional. For example, you have 0 to 100. This is 0 to 100, x and y axis. So if let's say whenever your value in x-axis is same as y-axis, so what will you get? You will get a straight line, right? You always get a straight line. If provided the value of x and y-axis is directly proportional. Directly proportional. If it is just proportional, perhaps you might get, curved line like this or curved line like that. Okay, but if let's say it's directly proportional, for sure the line is a linear line. Okay, So this linear line is also, I mean, the same rules is applicable to three dimension, whereby you have three different exit like X, Y, and Z, so-called. Okay. So, but in this case, we have a R, G, and B, like representing R, G, and B. Okay. So X, Y, and Z is just to mention the dimension. So that is the reason why you have a three same value here. Because if any of these exit is not directly proportional, you will not get a grayscale. You may get something, for example, like you have 100, 100, and 200, or maybe not so severe, like 100, 100, and 105. So you might be more towards either side, no matter it's red, green, or blue. You might be more biased to that side. Okay, so you will not fall within this one. And then for sure, this is not no longer a grayscale. Okay, so this is the reason why you have three different value in MATLAB. Okay, not simply just the MATLAB is lazy and display you three same value instead of three different value, or mute away green and blue, something like that. Okay. So but nonetheless, although you have red, green, and blue, and the effect that you change from, this is another case. The effect that you change from, you have a RGB color and you change into red channel, green channel, and blue channel, and you apply whatever image processing technique, and you compare with the RGB, which convert to grayscale, the effect is different. That is because each of these channel might have some information might be more sensitive towards or more biased towards a specific channel. For example, if you have a red color pepper, the red color all the outlines or all the features might be more prominent in the red channel, but less likely to appear in blue channel or maybe green channel. Usually, green channel for those red color stuff will appear with dark color, maybe dark gray, something like that. Okay, so might not be so um significant that, yeah, usually is I wouldn't say that it's a noise, but that is the behavior. Okay, so I think after the lab and assignment, you all know this one, right? So after you apply the image processing in different channel, especially in age detections, and if you compare with RGB image convert to grayscale and apply the edge detection, the effect is different. Okay, so that is also another case which highlight that applying the image processing in respective channel would have a better result when you compare with just converting to grayscale alone. Because when you convert to grayscale alone, some of the information might lost. Okay, not really lost, just that some of the information might be normalized out, rules out already. Okay, so CMY based on the subtractive mixing. Why it is called subtractive is that it's minus something else from the white color. Okay, so use the property of ink to absorb certain color. Instead, color addition, color subtraction is done. Color subtraction. For example, yellow ink subtract blue from white. Okay, you have to know this theory because it's important that you can differentiate that what is a so-called additive versus so-called subtractive. So CMYK scheme is widely used for color printing, especially. So we can invert the invent to specify what ink density to lay down on paper to make certain desired RGB. So you have your CMY color pigment, you have your white color light, and RGB. So basically, you just rearrange this one, you will get the RGB that you want. And one minus by your C, M, and Y, cyan, magenta, and yellow. So it's good because as I mentioned, not a must all the answers should be in point form. Uh, of course, I would recommend you all write in point form. First of all, it's easier for me to highlight the point. The second thing is that this is not assignment or pieces or whatever. So it's okay for you to write in point form. Okay. And nonetheless, if you want to write in paragraph, it's up to you. But make sure your writing is readable. Okay. And if you want to edit your answer, you can use all these equation is welcome. Okay, it's up to you to use. Um, it's okay. I would take this I mean, I would accept this or this kind, but make sure you give some explanation over there. You don't just put for example, erosions. You don't just put a formula for erosion, that's all, and you explain nothing. And the question is actually, 4 marks, something like that. So I'm not sure how to allocate marks for you. Okay. So be extra careful on this one. Incident white light coming in, and then a layer of cyan ink on the surface, and absorption of red light, and then emerging light. So usually you have an eye over here. Okay, so you would observe what color is this. Okay, and you can explain using this such a way lah. You have RGB, and since this is subtractive, you have a 1 and minus by CMY. So basically this one. Okay. And always remember, after you write in such a way, you have to mention what color is it. Okay. Do not just write, in such a way, but without mentioning what is this color. I know this is 0 portions of red, one for green and one for blue, but what color is it? Okay. There are several cases lah. This is one of it, and this is another lah. But the theory is the same lah. Okay. So this is the RGB and CMY color model. But I think if you can memorize, I mean, you don't really need to memorize this color model. But actually, this is exit, not really a cube alone. Okay, so this is black color, this is white color, and this line would be grayscale. And you can actually change uh to this one CMY cube. Is the same, but make sure you don't simply just change the value of this one with this one, when you have RGB to CMY. That is because the value in this model, if you have 000, it should be white colored, but 111 is black color. Please do remark on this one. But in the RGB color model or the color cubes, 000 is black color. I mean, as what we know, like, or as what we know all about. And 111 is white color. But this is inverted when you're in the secondary color model, which is CMY. So as the cyan, magenta, and yellow are mixed, then all the RGB color are subtracted and the black color is obtained. However, in practical, inks are not pure, so hence a special care is added. So HSI, HSV, and HSL are a cylindrical coordinate representations. So the same lah, the same to the RGB, just that the way to define this color model would be a bit different. So this is the uh, HSI. So you have a hue, saturation, intensity, and uh, most of the I mean most of the content of this color image would be described by hue lah. Okay, um hue would be defined in terms of degree. You have a center point, you have a triangle, so it depends on what angle it is. Okay, different angle would have different color. And you have another thing is the saturations, which is located at the center. It depends how saturated is the color. Okay, if let's say it is approaching to the center, which means not saturated lah. If it is approaching outwards, it's more saturated. Basically, it's something referring to this one. So this is zero saturation, for example. And then let's say extending outward, so you will get this color of red. Extending outward again, you will get a better color until here, which is fully saturated with red color. This is yellow color, which is the intermediate. Green color, um blue color, magenta color, cyan color. Okay, so this is this line extending outwards is referring to saturation. And this line in vertical axis is referring to the intensity. So you have if you move toward this part would be white color, and move towards this part would be black color. What is the reason that this cone in a cone shape, like a diamond shape? Why is it like that? Because when you approaching to very, very bright color or very, very dark in color, the color range is tend to, I mean, narrow down. Okay, because you don't have so many variety when your color is very, very bright. You know, you have a pale or very pale white, or sorry, pale red, pale maybe blue and etc. Or very, very dark red, dark blue and etc. But you don't have so many different degree of dark. So that is the reason why at this point, I mean, on both of these extremes, it is more likely to be reducing in the color range because the choice of the color is reducing. And the widest color range would be here, which is 50%, 50% of white and 50% of black. Okay. And yeah, the idea of this I mean, would be more or less similar, just that the center one is a circular shape instead of a triangle. So again, you have the intensity, hue, and saturation. The idea behind this one, the hue, the saturation, the intensity is remain unchanged. So table below, okay, you don't need to memorize this one, but nonetheless, this is just FYI lah. I mean, you should know how to, I mean, the background theory, how to get Q is based on degree. Okay, it's not in something else, not cm, not distant or whatsoever, but based on degree. Okay, um, okay. So this graph is actually explain the why it is in cone shape. You can actually view entire this, maybe this part lah. You can actually assume it's this part. So when you are going, I mean your intensity become darker and darker, you would expect you have a lower range of value because you see, even though here and here is more or less the same, you're still able to see some red color here and perhaps some red color here. But in here, our eye is basically not really can differentiate. And then at last, full black. Okay, the same thing apply here. So when you towards the, I mean outwards again, when you move this box upward, maybe somewhere around here, you will have the same hierarchy, which is this box would be totally white lah, and then white, 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 and then maybe pale, very, very pale, something somewhere around this one lah, which is more likely like a very bright pink color and etc. So HSI's model is a hexagon subset of cylindrical coordinate system. So the eye can see about 128 different hue and about 130 different saturation. So you have a very wide range lah. Mm. So whenever as I mentioned before, whenever you see the approximity, sorry, it is so-called the normalized value lah. So make sure when you have, for example, you have 126, so make sure you divide by 255, sorry, 255 first lah. Okay, make sure you divide by 255, not 256 because if you have 256 so 255, let's say the value is 255 lah. 255 divided by 256 is not equal to 1. Okay, I know the total value is 256, but in order to normalize it, the maximum value should be the value available in your system. Okay, so since your system is only have 255, the maximum value, so I mean the denominator should be 255 instead of 256 lah. Okay, not the n number, but instead the maximum value you have. So for all these, remember to normalize it first, and then you would be able to get the data. Data is the uh, angle for HSI. So color video, color model on video. Methods of dealing with color in digital video is largely derived from older analog methods coding of for TV. So as our eye is more sensitive towards the luminance and not so sensitive to chrominance. So we have so-called a subsampling. Okay, we have learned the subsampling, for example, 444, 420, 411, something like that. So when you have all these kind of subsampling, Why the reason why we have all this subsampling is that our eye is actually not sensitive towards the chrominance channel. So it's okay to remove part of, I mean, most of, I would say most of the information in that part lah. Okay, and retaining whatever which is more likely useful to us. Okay, so you have your Y channel, which is the luminance. So we are more likely to be, I mean, our eye is more likely to be sensitive to luminance lah. Okay, which means uh, you have a when you convert your when you try to convert, you can test of this. You can try to convert your RGB to YUV, and then maybe YUV or YIQ or YCB size. Okay, you will find that CB and CR is more likely to be color range instead of the ages, the texture, and etc. Usually all this information will be in white. Okay, so that is why try to we will try our best to optimize whatever value we can retain. I mean, at least useful to human eye in Y channel, and remove all those redundancy informations in the Y channel. So that is how we perform the JPEG lah. This is the core tenet of the JPEG. So you have to know why we only apply in Y but not CB and CR, and why we only apply subsampling. Because subsampling actually remove quite a lot of information. Of course, with 444 we remove nothing. But in 420 or maybe 411, we actually remove up to 50% or maybe 75% of the original channel. So it's important for us to know. So chrominance refer to difference between a given color in a television picture and a standard color in the same luminance. So most TV video use a matrix form called YCBCR, where we already know, and related to YUV58. So this is another standard. So we have learned all these two standard especially in the video processing, NTSC and PAL. So for different NTSC, PAL, they have their own lines. I'm not quite sure what is the exact numbers, but it should be in the chapter 11. So for all that number would be those line available to perform the progressive or interlaced scanning. So let's say you have a full range, for example, let's say 5 7 something, 5 7 6 5 4 6, I think. Yeah, we need to double check with chapter 11. But not all these lines is available to display the lines in terms of the no matter it's progressive or interlaced, but only part of it is being used, and then the rest of it is meant for multimedia data or other controller system. Okay, so you have to know these informations, and the main difference between the two format are based on their electrical difference, resolution quality, and the rate at which broadcasts are displayed. This is usually regulated by based on regions. For example, Europe regions, Asian, and etc. Because we are sharing most of the we need to standardize the information. If not, a lot of conversion need to be done when we try to source any um, signal from from other country which is not in the same region. So we need to standardize it so that we can reduce the workload of to standardize or maybe to perform the conversion itself. So this is the basic analog TV and digital TV, the video format and color model. So ViuV is the color format used for PAL. And YUV color model is represented by one component of luminance and two components of chrominance. So again, our eye is more sensitive to luminance and less sensitive to chrominance, because chrominance uh, consists of the information of color, and luminance consists of the um, information of brightness. So YUV color model of video separate RGB into Y, U, and V. The reason why we need the reason why we don't use RGB but we use YUV is that because RGB is not, I mean, not applicable to such. I mean, you cannot perform subsampling in RGB. The reason is that the value in RG and B must be managed or processed in the same scale. For example, whatever you perform in red channel, you must perform in G and B channel. If you only perform in red channel, but you did not perform in G and B channel, perhaps you might have a lot of different kind of syntax issue. For example, you scale down the R, maybe originally 300 times 300, but you scale down the R to 100 times 300, but remain unchanged G and B. So when you combine later on, for sure you cannot combine. That is because you cannot simply just process only one of the channel and ignore the rest of it. So, but in YUV, you can do so. That is the logic behind the JPEG compression, right? You scale down or subsampling the chrominance channel, but you process the luminance channel, which is the Y channel, by using a series of Fourier transform. So that is the reason why we are using YUV or maybe YCBCR instead of RGB, because RGB not really allow these applications, and we actively seek for a good trade-off between the quality of the image, no matter image or video, and also in terms of storage size. So human eye is more sensitive towards the Y component or luminance than U and V. So that is why we perform subsampling, which tends to eliminate up to maybe 50 to 75% of the information. So in order to reduce the video size, the Y component can encode it with higher resolutions compared to U and V. Historically, the terms YUV or Y prime UV were used for the specific analog encoding and color informations in television system. So YCBCR was used for digital encoding for color information, suited for video and still image compression and transmission such as MPEG and JPEG. So today, the term YUV is commonly used in the computer industry to describe file format that are encoded using YCBCR. So Y is actually the luminar component, and UV are the chrominance component. And this is simply just the luma lah, okay, which means denote the gamma compressions. Basically, when you saw the Y prime, uh, except elsewhere mentions else, it is referring to normalized, okay, which means from the range 0 to 1, okay. But of course, you have to check because not a must in such a way. If let's say being mentioned elsewhere, so make sure you follow the commands or rules and regulations. So the conversion formula is given by a weighted sum of the R, G, and B, which is this one. Um, yeah. So this is how you convert RGB from, I mean, to YCBCR or YUV. But nonetheless, always remember you have your prime here, which is, I mean, normalized to a range 0 to 1. And again, the informations, I mean, the equation is not given in the final exam. So for gray pixel R is equal to G is equal to B, and the luminance Y is equal to the same level of R, since the sum of the coefficient of this is equal to 1. Okay, is equal. Okay, thus Y that represent the luminance can be thought as of contain grayscale intensity, and U and V carry the chrominance. So that is the reason why whenever you convert to YCBCR and you extract the Y value alone, you will see a more likely like grayscale color because of this reason. So this is the formula. To actually you can organize this formula into matrix form. Nonetheless, whenever you have something like this one, it is in matrix lah. Okay, this matrix is very important in um many engineering rules, no matter in MTA, image processing control system is very important. So whenever you want to establish the equation, you can always transform. I mean, for simplicity, like to calculate or to especially when you calculate using software like MATLAB, it's important for you to transfer it to matrix form. It's easier for you to calculate. Of course, you need to comply with some rules and regulations, because when you define something else, when you transfer to matrix form, you have a specific rules for you to follow. I mean, how to extract the RGB, put in the value for YUV. So this can be read at this one, and then this is the equation. I mean, how actually you derive this one. So one goes back from YUV to RGB by inverting the matrix. I hope you know how to do the inverse matrix inversion transformation. Sorry. To obtain the grayscale image, simply convert each RGB pixel to YUV or YIQ pixel and keep the luminance channel and discard its IQ chrominance channel. Luminance channel is the Y. So this is the original color image. So after you perform the conversions, you would more likely to see the Y channel is the Y prime channel or Y channel is more likely to be not exactly lah. Of course, when you just based on human intervention, it's more likely to be more or less like like the grayscale image. But in fact, in terms of some color images, it might be different. Okay, and U and V is more likely to be color based lah. Okay, and YIQ is used in NTSC, one of the color scheme, the standard. Again, the gray pixel generate zero IQ combinance signal. And although U and V are very nicely defined, they do not best correspond to actual color sensitive to human eye by UV. Okay, in NTSC, I and Q are used instead. So um, it is sometimes depends on the choice of the committee, especially to decide what is the color channel to be used. Because for some um because for this one somehow is a bit qualitative. Of course they will not only just simply say, oh, we choose YIQ, like there must be justification over there. And as I mentioned before, it's more on the electricity, the compliance to rules and regulation and etc. But nonetheless, the part of the justification is that the YIQ is would I mean might be a bit superior than YUV lah. So that is why in terms of the NTSC, they select YIQ instead of YUV. So YIQ, sorry, YIQ is just a versions of YUV, just that the Y is the same in terms of Y, but the U and V are rotated by 33 degree. Okay, so this lead to a formulation of this one. So this is the uh, difference YUV and YCBCR. The REC 601 standard, another standard. I think I did mention in the I think I did mention in chapter 11, and also the tutorial. I think the tutorial we have this question as well. Yeah, tutorial have this question. For digital video, use another color space, which is YCBCR model, which is closely related to YUV transform. This make the equation of CB is this one and the CR is this one. Okay, and YCBCR transform is used in JPEG compression and MPEG video compression. Basically, YCBCR is the core uh, channel that we use in JPEG and also MPEG. Okay, uh, especially for because JPEG is meant for static image, right? And MPEG is for video. So whatever, as I mentioned before, whatever applicable to image, especially static image, is applicable to video. Just that it depends on which type of compression it is, temporal or within the image. If it is temporal, they might be use the motion estimator to estimate uh, the next motion, so called. That's why you have the uh, I frame, P frame, and B frame. But for this, I mean, within one static image, you might use the same or maybe something else which is similar to whatever compression you apply in static image. So the most common one would be JPEG lah. Okay, so you can perform um, temporal compressions by using the motion estimator, and within the static image you can perform JPEG compression. So these are the common compressions in terms, I mean, in the video processing, and in image processing we only have the static one, which is JPEG. Okay, but nonetheless, of course, JPEG and also the MPEG compression is not the only, I mean, not the only compression available, but it's actually have a lot more compressions method available. Just that these two are the, I would say, bottom line lah, okay, and most widely used even until today. So that is why our computer, we always can play MP3, which is layer 3 MPEG. We can play, I mean, we can save at JPEG, but it's very rare for you to save at JPEG 2000. Okay, so this is the difference. Okay, most likely is because not really because of the capability of this of this algorithm itself, but how popular it is to the public, and yeah, this affect the choice of the affect the choice. I mean, the manufacturer lah, the decision from manufacturer as well is affecting as well. So since JPEG is more likely to be populated among common society, so instead of JPEG 2000, we are using JPEG. Okay, so that's all for this chapter, and yeah, see you all later on for the tea. If you have question, you can raise later on. Okay, do you have any questions for today or any other relevant questions? Okay, I suppose none. So see you all later on for 30. We have tutorial class today. Okay, and that's all. Bye bye.